Okay, so today we're starting matter, density, and relative density. So let's go up to the objectives that I have that are listed here in your ILM. It tells us we need to describe some common states of matter. There's 3 of them that we need to be concerned about. We're going to define some terms about matter, elements, compounds, and mixtures. We're going to define terms of adhesion, cohesion, surface tension, capillarity. We're going to then do some calculations according to density, mass, and volume substances. And we're going to calculate mass and density using relative densities. Okay, now they have a little bit of this introduction here. And this is the basic concepts for the understanding the concepts of pressure, buoyancy, and electricity. I don't know about that, but you know, it's good to have a foundation of anything, especially when we're talking about some science stuff. So let's just start on objective 1, where 3 states of matter. The 3 states of matter that we have to be concerned about. The first one that I'm going to talk about is right here. It's solids, right? We're going to talk about solids. And solids, if you did not know this, and I don't know if you knew it or not, they have a definite shape, they have a volume, and they have a mass. Okay? That's pretty straightforward. There's nothing new there. And then we have some terms associated with these. First is brittle. And brittle is to bend without breaking. So will not bend without breaking. Sorry, I got that a little mixed up. Have you ever seen drainage cast iron? That's brittle, right? You drop that from a 1-foot drop and you're going to break your cast iron pipe or even the fittings, right? We know that. Is that true? That's true. Ductile, maybe stretched or drawn into shape. Sure. And then there's flexible, easily bent without breaking. And then there's malleable. Malleable can be beaten or rolled or squeezed into shape. And so those are some of the terms that we associate with solids, right? We associate those with solids. Jan, I see you're still laughing. I mean, you can't even get over yourself there. Okay, the next term that we have to be concerned about is one of the 3, and that's liquids, right? Liquids have this indefinite shape. They take the shape of the container or whatever they're in. They have a definite volume and a definite mass. Now, as you can see, we could probably tell that everything has a mass. So yeah, thank you, Taylor. So those are the 3 terms that we're going to associate with liquids, all right? And now there is some terminology that we have to talk about when we're dealing with liquids. One is adhesion. Now it says here in this book, unlike molecules, stick together. So what they're talking about adhesion, they have some illustrations a little bit more in this book, and we'll talk about how water sticks to surfaces, etc. And so we'll talk about that. Then there's that capillary action. I think we've even talked about this before in welding fab. It's the tendency of adhesive liquids to flow into small cracks, solder into a flux joint. Okay, so we're going to do that. Cohesion, it's when like molecules like to stick together. Mercury, for example, is very cohesive. It's like the T-1000 Terminator. I don't know if you guys remember the Terminator, the liquid metal guy. It's like mercury. Have you ever played with mercury before? No? It's dangerous. Keep it in. Don't play with mercury. Don't eat it. Don't put it in your mouth. Don't play with it in your hands. It's toxic material. So we'll talk a little bit more about mercury and its properties coming up. Fluidity, that's how that you say that word, and it's the ability to flow. Incompressible, incompressible. Wow, that's a big word. It cannot be compressed. You know what is not compressible? Ooh, how come that's there? Water. You can't compress water. Listen. What?
Is that true of all liquids?
No. But water is the one we're going to be concerned about mostly, Kristen. Some fluids can be compressed, but actually, listen, most fluids can't be compressed, right? They could be put under pressure, but you can't make them smaller. You can't make it smaller than it is. How's that? Okay. Viscous. Viscous is the next word. It resists shearing or flow. And then this surface tension. It's that surface skin that forms on liquids due to those cohesive forces. So the next one that we want to talk about is gases. Okay, so this is the third one. We talk about gases. And now gases have an indefinite shape, indefinite volume, but a definite mass. And these are the terms that we need to know as we're dealing with gases. And they are over here on this page. They are compressible. We can compress gases, and that's how we use most of them in our ability. Yeah, Alex, for the bad jokes, I will stop. They may be compressed. Now, pressure increases, volume decreases. You see this dichotomy here, this difference. Pressure increases, volume decreases. So as you increase the pressure, you can get that gas into a smaller container, is what it's saying. Okay, that's what that means. Diffusion. So diffusion is now a diffusion also can be in a commercial application where you have diffusers in the ceiling, and there's those big it's like a big vent that blows the warm or cool air around the room. It's a diffuser. Okay, that's what that is. And the next one is fluidity. Now, we saw fluidity for fluids. Gases are also considered as a fluid or in a fluid. So they move according to their densities, either low density or high density, which permits these molecules to move quickly and randomly. Like heavy gases like H2S flow to lower areas. And we're going to talk about gases, and we're going to talk about relative densities of gases, and we'll talk about that as we get into some of this stuff. So having said that, we're close to a break. I'm going to pause, and that brings us to objective number 2, which is define the terms matter, elements, compound, and mixture. So the structure and behavior of matter. Can everybody see my screen there? Okay, so there's some boring stuff in this couple of next pages. Now, we talk about molecular theory. Now, do you know why we never trust Adam? Because he makes up everything. I don't, you never trust an atom. No, that's not good. Come on, that's funny stuff. That's an old dad joke. That's pretty funny.
I'm writing that one down.
Yeah, you should. Yeah, keep that one in the bank for about 50 years, and then you could pull that one out again. All right. So now everything down to its smallest is a molecule, and other parts are atoms. Okay, but what we really want here is we want to know, I don't know why I'm zooming in and out here. What we really want to know is that everything has a mass. Everything has a mass, okay? You can't get away from it. Now, an atom is the smallest unit of an element and can still retain its properties. Now, if we go on through in the middle here, we talk about protons and neutrons in the center. See, they have down here neutrons and protons, and then they have these electrons orbiting around the atom. It's kind of like our planetary system, quite frankly. It's almost identical to our planetary system. It's like we're on a small atom drifting into space. I mean, am I the only one that thinks that way? Sometimes I think that way. So anyhow, let me erase that. So as you can see, if you get an extra electron, you see electrons are negative and protons are positive. That's kind of important as we move along. Remember that protons are positive and electrons are negative. All right, you got that? Beautiful. Then we're going to talk about elements. Elements are, you can't break down an element to anything smaller. That is all of it. It's a one kind of atom and it's an element. Now they go on to, why do they even put H2O in there? Is H2O an element? No, it's a compound. H2O is a compound and it has two separate elements coming together, hydrogen and oxygen. Okay, so some of the elements that we're familiar with are gold, copper, tin, lead, zinc, iron, mercury, hydrogen, oxygen, nitrogen. And then the 100 or so, I think there's about 118, there's metals and non-metals. And I remember, I think I showed you guys a table of periodic chart or elements, periodic table of elements. I think I showed you one at one point. Okay, so metals have many properties in common. They are generally good conductors of heat and electricity. What makes something a good conductor? Does anybody know? So what makes metals a good conductor? For example, copper. So if I had elements of copper, it has these actually little free electrons attached to it. So what happens is these little electrons, they're negatively charged. They have this little extra electron. So when we introduce electrons into a copper wire, they transfer very easily. Let me just move this over because you won't be able to see this on the recording. They transfer very easily and they go and they keep going and they keep going and they keep going. So it actually transfers those electrons. If we push them in, they just bounce. They just move through very, very fast and very rapidly. And the same thing for heat. When we add heat to metals, they start to transfer by vibrating. These electrons start vibrating and they move along and they will transfer that heat depending on their vibration. Now, it is a way we measure temperature. We measure temperature. Let me just pull this back a little bit. Measure temperature through molecular movement. So for example, if I had a thermometer, that's a really poor looking thermometer. If I had a thermometer, like a mercury bulb thermometer, and it looks something like this, and it has a bulb on the bottom, and if it was filled with mercury, right? And as that mercury starts to get warmer, the molecules start to expand and they will start to move upwards in the tube. The hotter it is, the more vibration you will get of those molecules, and it gets higher and higher. And we just simply put a scale on the thermometer, and we're measuring actually molecular movement out of a thermometer. Okay, it's really all it is. So that's kind of how a thermometer works, if you did not know that already. But you guys are pretty smart. You probably all know everything already. And if I do this, and I said that my eyes are blue, does that look like my eyes? No? Okay. Let's move on. So a compound, here we go. We're talking about compounds now. Now, a compound is when you have chemically joined two or more elements. Now, the most abundant compound on Earth is water. Water is the most abundant compound on Earth. We're going to go for another 6 minutes and then we'll take a break. Okay. Now, the compounds that we use in our, pipe trades, natural gas. Its compound is CH4, meaning it's 1 carbon and 4 hydrogen. Propane, C3H8. Butane, C4H10. Okay. So those are the hydrocarbons. They call these hydrocarbons. Hydrocarbons. Because we have hydrogen and carbon. That's why we call them hydrocarbons, and that's what we burn for our power, for our heat, for a lot of different things, and we get a lot of byproducts off of these things, right? Now, a mixture, a mixture is a combination of different molecules, but they're not chemically combined. A lot of these are like alloys, where we have like brass. Brass is a mixture, because if I melt down brass, I will get the properties. I will get the copper and zinc or tin. I will get them separating. So they're not chemically joined. They're just a mixture put together to make something different, an alloy, if you will. Okay. So it's like one of your favorite drinks, right? Rum and Coke. That's a mixture. It's not a chemically combined compound. It's a mixture. All right. So that's what that is. Now, solution is the next one here. Solutions are a special type of mixture in which one substance is dissolved by another evenly. So if you ever put hot water with the Jello packet, and you dissolve those Jello crystals into that water, you make a new solution with those two combined, right? Water is considered basically the solvent, the universal solvent, if you will, because it actually cuts down a lot of the toxicity or levels of anything in it. So we want to, dilute something. We typically use water. Yes? Any questions? Is that page 5 coming over here? Yeah, page 5 and page 6. All right. So that's not too bad. Now, two factors that determine in which state matter exists are temperature and pressure. Those are the two biggest things. This is really big. Temperature and pressure affect, wow, everything that we do. Okay? Temperature and pressure affect everything. And I'm going to stop right there because there's a couple of things I want to say about temperature and pressure before we continue on. But I do want you guys to take a 10-minute break, come back at 10 after 10, and we're going to continue with more of this science stuff. So where we left off is we were talking about temperature and pressure. So I wanted to pause there because I'm going to talk about a little bit about temperature and pressure. Okay, so now I'm back to my screen where we left off on temperature and pressure. Now, I want to write down a couple of things here. So please take some notes here. Let me just get a black pen. Okay. I want to talk about STP. Does anybody know what STP is? And it's not Stone Temple Pilots. Okay, just so you know. STP is standard temperature and pressure. That's what STP stands for. So first off, we're going to talk about standard temperature. Now, standard temperature, so listen, I just told you that temperature and pressure affect all state in which matter exists. I just said that. And that is true. And we need to know what a standard temperature is, because any of these calculations that we're going to do, any of these volumes and capacities and relative densities and everything else, we want to have a standard temperature in which we're dealing with, because temperature affects everything at which we are dealing with. So, for example, if you are at the gas pump and you're putting fuel in your truck or your car or whatever, or your moped for you, Alex, if you're putting fuel in your vehicles, and if you look under the gas pump, right under the numbers where it says volume corrected to, and it gives you a number. Can anybody remember what that number is?
15 degrees.
15. Actually, so standard temperature is more precisely 15.5 degrees Celsius. So they want to sell you that fuel at a standard temperature. Because as you know, or maybe you don't know, but if this fluid is allowed to increase in temperature, it would expand, wouldn't it? And if it got colder, it would contract. It's kind of like the George Costanza law, if you know what that means. So I'm gonna share my screen still. So there is the standard temperature at which we do all of our calculations, and there is a equivalent measure to imperial, which is 60 degrees Fahrenheit. Okay, so we have to know that. So those are the two temperatures. Now I'm going to talk about standard pressure. So of course, pressure affects all state in which matter exists as well. So standard pressure is taken at sea level. And the pressure at sea level is, does anybody know that number by any chance? The pressure at sea level is measured at 14.7 pounds per square inch atmospheric. So the A stands for atmospheric. and sometimes the A stands for absolute. Okay, so two different things meaning two different words meaning the same thing. So that's what the A is in this. So there is a metric equivalent to this pressure, and it is 101 kilopascals. And that is a metric equivalent to that number. Now, there's also a mercury equivalent to this, and it is 29.92 inches of mercury. So Hg is the chemical symbol for mercury. And there is, under mercury, there is a metric equivalent to this 29.92 inches, and that is 760 millimeters of mercury. Now, it's really tough for me to kind of put that out there without giving a little bit of an explanation on how we come up with that number. Okay, so we're going to do a little sidebar in and how we get this pressure and how we get what this weight of the atmosphere, because that's what this is right here. This is the weight of the atmosphere that is exerted on us at sea level. Okay, that's what that is. That is the weight of the air at sea level. So when I'm here in Alberta, my golf ball flies farther in Calgary than it does when I'm in Vancouver, because the weight of the atmosphere here is less than that in Vancouver. So I'm going to tell you a little story here. So there was this guy that had a bowl, and he took this bowl. Oh my gosh, I can't draw worth the beans here. Let me just get this a little better. So he so he took this bowl. He had this big bowl. Let me make it bigger. There we go. He took this bowl, and in this bowl, he put a tube in it, and he filled this. He got this tube with a closed end, and he put it in the bowl. And then in this bowl, he filled it up with mercury. And he put this tube full of mercury in the bowl as well. What he did is he put his thumb under it, and he put that tube in there, and he supported that tube in a full bowl of mercury. And what he figured out is that the pressure exerted downwards on the mercury kept the mercury up the tube. It kept it sitting there. And it actually sat there at a measurement of 29.92 inches. So he determined that the weight of the air pushing down on the mercury in the bowl kept it going up at 29.92 inches. It's kind of cool. And what he also did, was he took this little contraption he made and he went up a mountain. So let me just draw a mountain here. There. So this guy took his little contraption and he walked, so he had his bowl full of mercury, and he took it up the mountain. As he went up at higher elevations, he noticed that this mercury level started to drop. So he determined that the higher he went up the mountain, the less atmospheric pressure was pushing on the mercury. So he determined that higher elevations, less atmospheric pressure is exerting on you. Now, it's not a huge, hairy deal, but we need to know this for a couple of different reasons. And one of them is that fuel gases burn differently at higher elevations than they do at sea level. And he noticed something else about his little Mercury contraption here. As a big storm cloud came over the horizon with lightning and everything else. So let me just draw some lightning. Oh, look at that. I am just a brilliant drawer of things. And, you know, and all the rain that came with it, he noticed that this started going down again. So he determined that a big storm actually incurred a lower pressure, right? And then once the storm went away and the sun came back out, he noticed that this mercury in this tube started going back up. So he equated that sunshine was higher pressure in the atmosphere as that came out. And he started to predict the weather with this, because you know what this guy created? This guy created the now known the barometer. And that's how he did it, is with this little pressure thing. And this guy's name was Torricelli. And this is the guy that created the barometer, and he actually determined how atmospheric pressure is exerted over the Earth at different locations. Kind of a cool kind of side story, huh? So it was Torricelli that did this. I don't know where all these Italian guys got so smart. I don't know why, but there you go. Okay, so that was a little extra. So let's go into, where are we here? Our next port. We're talking about a physical change, chemical and physical changes in substances. Okay, so we know substances are continually undergoing changes, and there's two kinds. There's a physical change and a chemical change. So a physical change does not affect the chemical composition. A chemical change produces a new substance or something with a different chemical composition. So they give you some examples down here of what that is. Okay, the Renaissance, Jen, is how they got so smart. I don't even know how. Anyways, let's go to the next page. And oh, the next page, I don't know where the next page is. I don't have page 7. What's page 7 in there? Not sure. So we're going to talk, the next thing is when you fill water in a tube, if you have water, okay, that's important, water in the tube, a water will exert adhesive forces, and water will tend to make in a tube, will tend to make this kind of meniscus. This is what this is called, a meniscus, because its adhesive qualities, it creates a meniscus that is concave. Okay. So you get a concave meniscus. You get a concave meniscus when we're talking about water. Okay. So we use sometimes these tubes to indicate levels of pressure, and you always have to read the bottom of the meniscus. Okay, you can see here this line. This is the bottom of the meniscus. You have to read the bottom because that's where the level is. It's just the adhesive qualities that gives it that concave look to it. Now, we have the next piece where it shows we have Water, can you see water here has a meniscus that is concave. And then it shows mercury over here. Mercury has a different kind of meniscus. Mercury has a convex meniscus. When you have mercury in a tube, and if you have a mercury thermometer, you could actually see that it has a convex meniscus when it's in a tube. This little scale here is a manometer. And this manometer is used to measure small gas pressures. So what they do is they hook up this manometer on one end to a gas outlet. And that gas pressure will push downwards. And this is a U-tube manometer. This will be connected down at the bottom, and it'll push gas downwards, and it'll push it upwards. And then you have to have this at 0 when you start, for sure. And then you measure both sides. So you measure this side at 1, this side at 1. So you have 2 inches of water column, or 2 inches of gas pressure. John, that's where they came up with Americana. If you go to Starbucks and you ask for that, it's espresso mixed with water because the Americans couldn't handle the strong coffee. So mercury with this convex meniscus, mercury, it's because mercury is cohesive. Now, cohesive. Mercury is cohesive. Mercury is cohesive. Remember that. Water is adhesive. Water adheres. Okay. Now, surface tension. Remember, we mentioned surface tension. We talked about gravy, but you could also see, you could also put a pin on the water and it will float. You ever see those bugs sitting on top of the water? Bugs have this, that water has this surface tension on it that these bugs can literally float on top of the water because it has it. Now, this is a cohesive force, not to be confused with what the mercury is. This surface tension that they're talking about has a cohesive force. Okay, so don't confuse that with the mercury. Now we're going to move to the next page, page 11, I believe. Well, there's page 9. Oh, there's the page 9 I was looking for. And there we go. We talked about adhesion. And there's adhesive properties of water, and it shows it has a concave meniscus. And then we have cohesion, and they talked about mercury in cohesive forces, and then you have that convex meniscus, because mercury likes to stick to itself. It likes to stick together. It is the T1000. All right. And now we'll go down to page 11. And we talk about now that capillarity. Oh, look at this picture. They have water surface. As you can see, they overfill. Nobody's ever overfilled a glass, eh? No, I've done it all the time. Make a big mess. Okay, so capillarity is also called capillary action. And it's the ability of these liquids to rise and drop in small spaces, right? And it has that ability to do that. And the smaller or tighter the opening, the more fluid will rise or fall. And we talk about soldering. on capillary action. And then it shows some capillarity from different things. But here we go. Now, soldering, as you can see in here, so if we have copper pipe, and if this was copper pipe in here, right, and we have this hub fitting, so you can see how it has a hub fitting. Now, there's a couple of things that happen here. So the application of the flux aids in the capillary action and promoting of the wetting action on the surfaces. So if anybody has ever tried to solder copper pipe together without flux, what happened? Anybody say? Your solder falls to the ground. It doesn't stick, right? Nothing sticks. So in a copper joint, if you have, so if I'm going to use purple as my flux, as you heat up this joint with your torch, the flux will get liquid and will start to run down the pipe. And if you don't wipe that off, your solder is going to follow that flux. So a couple of things happen in capillary attraction. You have the capillary attraction and you have adhesion happening as well. You have two things in soldering. Because this adhesion, you put flux in there and the solder sticks to where the flux is. In this application, it sticks there. So you have the flux as a wetting agent, wetting that surface, not getting it wet. It's something where the solder will stick to. And then we have a little summary on here that you guys need to know. Okay, so that's just talking about all of those things: cohesion, adhesion, surface tension, capillarity, and that. Which brings us to, does it bring us to density? Oh my gosh, I'm so happy. Which brings us to density. Now, density is the mass of a substance per unit of volume. So this is really important right here. Mass per unit of volume. So we kind of started talking about those if you don't already know. Can somebody tell me what is the mass of 1 cubic foot of water? You remember? Anybody?
Isn't it 62.4 pounds?
That's right, 62.4 pounds per cubic foot. Is that not correct? That is right. How about 1 inch? I'll write it. How about metric? How about this one? How about this one? Okay, this is imperial. This is excited states. So these are by definition densities of water. Density by definition is a mass per unit of volume. Look at mass, volume, mass, volume, mass, volume, mass. A gallon is a volume, mass, volume. This is by definition densities of water. Okay, so that's what those are right there. Now, we can calculate densities by using this formula triangle where mass, M, is equal to the mass, and the mass is always in pounds or kilograms. Mass is a weight, okay? And we can then divide that by the volume, and the volume is always in inches cubed, cubic feet, cubic meters. You get the idea. It's a volume and it's something that's cubed. And then the density is always a mass per unit of volume. Now, we always have to now write down your units of measure before you do any as you do your calculations, write down your increments of measure behind your numbers. It becomes super important as we move through this stuff. So let's calculate the density of Doug. We can see how dense Doug is. Wait a second, that doesn't sound right. But let's do that anyways. Okay, so my mass is 175 pounds. Aha. My mass is you know, COVID is I live too close to my fridge. I work too close to my refrigerator, so that's why my mass is a little heavy these days. I mean, you know. And my volume, I'm going to tell you my volume. My volume is 2.5 cubic feet. Okay, so that's my height, my width, my length. I can calculate my volume. And so now we can calculate how dense Doug is by taking the mass, 175 pounds, and dividing it by, if we use our formula triangle, we divide it by 2.5 cubic feet. We come out and we have Doug's density at about 70 pounds per cubic foot. Now let me ask you this. Am I heavier than water? Does anybody tell me? Am I heavier than water?
Yeah.
Yes, you are.
Yep.
Yes, I am. So what that means is that,
You'll float.
am I heavier than water? So let me just fill up my little swimming pool here, and I will get Doug in the water. So when I go into the water, because I'm heavier than water, Doug sinks. Because I'm heavier than water, I will sink when I get into the swimming pool. And only if the swimming pool is fresh water. Okay.
Is that correct?
That is
Is it-
correct.
Is it correct to say that is because you're heavier than water?
That is absolutely right, Christian. That I'm heavier than water because I just proved it by calculating my density. I am heavier than water. I sink when I get in the swimming pool.
So
I
you're
don't
denser.
float. I don't float. But we'll talk about some relative density at a later date. So this is why I float. Now, let's do some other density calculations. All right. So for example, say if I had an object that weighed 3,500 kilograms, and that object had a volume of 8 cubic meters. Can somebody, or can you, calculate the density? Remember, our density formula where it's mass divided by volume is equal to density. So we take our mass, 3,500, divided by my volume, 8 cubic meters. Now, always, always, always. Metric stays metric. If it's imperial, it's all imperial. Jan, I sink. Sorry. If you wanted to know. If we go swimming together, Jan, I sink.
So do I.
Okay. And that's why, because you're heavier than water. Maybe it's
I mean, I
heavier.
can't swim and I'm terrified of water.
Oh, wow. Okay then. So the density of this is 437.5 kilograms per cubic meter. So that's the density of that object. Yes? Pretty straightforward stuff. It's pretty easy so far. Now, I'm going to shoot you a couple of more numbers here. So if I had a cubic foot box, so 1 foot by 1 foot by 1 foot, which equals to 1 cubic foot, and I filled this up with air, does anybody know how much that would weigh? That is right, Matt. 0.076 pounds per 1 cubic foot. That is the mass of air. So then we have to do a metric equivalent by 1 meter by 1 meter by 1 meter. So air as a metric equivalent is 1.29 kilograms per cubic meter. Everything has a mass, regardless of what it is. So having that newfound information right there, I'm going to ask you a question. Okay, what is the mass of air in a room that is 15 feet by 10 feet by 8 feet? So first off, let's get the volume of that room. So volume of this room is length times width times height. 15 times 10 times 8. Did everybody get 1,200 cubic feet? Hopefully. So there is the volume of that room. So now I know that from up here, from this information I just gave you, that 1 cubic foot of air weighs this much. So I know that I need to times that by 0.076 pounds of air for 1 cubic foot. And so 91.2 pounds is what the air weighs, because the cubic feet get canceled out. I'm left with pounds of air. So that's the mass of that air in that room. Give you a second to write that out. I'm going to ask you another question. Ooh, spelt that wrong. I'm going to ask you what the density of mercury is if in pounds per cubic foot if 1 cubic inch weighs 0.491 pounds. Okay, I want to know the density of mercury in pounds per cubic foot if 1 cubic inch weighs 0.491 pounds. So what I just told you here is that 0.491 pounds per cubic inch. I just kind of said that right there. And what we do is multiply that by how many cubic inches in a cubic foot?
1728.
1,728 cubic inches in a cubic foot. And that's going to come out to pretty close to the density of mercury of 848 pounds per cubic foot. Pretty close, 847, 848, yeah, right there. Very good. So I do want to talk more about more stuff. Like I have more to share with you guys. I kind of screwed around this morning and we didn't get enough done, which is okay. So we're going to pick this up on Wednesday, right where we left off. Okay. Now that latest assignment, density, matter and density, I posted the key on there, which not great, but if you saw it already, well, good for you. Happy days. I have changed it since. That assignment will not be due though today, okay? Because on Wednesday, I'm going to get through densities and I'm going to get through relative densities. So then you have 2 assignments to do for the week. All right. Is that cool? Bay, did you put in your chat your room, or do you want me to just leave this one open? I could leave you as the host or what? You're muted.
Don't we have shop?
Oh, not till noon, I don't think.
Yeah, we've got an hour.
Yeah.
Yeah, I'll post that.
You'll post something? Okay. For those of you who still have to put in your volumes and capacities assignments or whatever they are, do it today, now, during this next hour lunch break. All right, please do that. If not, I think I have the printed version of the assignment ready for you guys if you want to.